Welcome back to Functional Analysis class. In our last class, we discussed the introduction to Hilbert spaces. There we talked about inner product and inner product spaces. We equally gave examples of inner product spaces. In today's video, we shall be examining the proof of Cauchy Schwartz inequality. Cauchy Schwartz inequality is a very important tool in functional analysis, particularly when we are talking about Hilbert spaces. So let's quickly look at how Cauchy Schwartz inequality is proved. So let's start with the theorem itself. Let E be an inner product space. Let E be an inner product space for arbitrary elements x, y in E. The absolute value of the square of the inner product of x, y is less than or equal to the inner product of x, x multiplied by the inner product of y, y. So for this, equality holds. That is, this particular inequality will change to equality. Equality holds when x and y are linearly independent. If and only if x and y are linearly independent. So if that happens, then they're what? This inequality will change to equality. So let's examine the proof. Let's examine the proof. The proof. To start with, let E be an inner product space, and let x, y be an arbitrary element in the inner product space. Arbitrary. Okay. Now, for let's say any z, that is coming from the complex number, and that z is arbitrary. Let's put it this way. For arbitrary z, let's write like that. For arbitrary z, that is a complex number z, and the absolute value of that z is 1, such that z multiplied by the inner product of x, y is is equal to the absolute value of x, y. Okay, so it's equal to that. Now, suppose from here now, A is equal to the inner product of x, x. B is equal to the absolute value of the inner product of x, y. And C is equal to the inner product of x, x. Let's suppose that. Now, for arbitrary T, which is a real number, we have that. That is for any arbitrary element T, and T is a real number. Let's say we have, let's continue here. An arbitrary element, a real number t in R, we have 0 less than equals to the inner product of tzx plus y, comma tzx plus y. Now this is simply going to be equal to, that is, we are trying to multiply this and this together. Normally, if we expand this in the algebraic sense, it will be saying that tzx plus y multiplying tzx plus y by algebraic expansion. So, which is going to give us what? Let's expand out. Tzx times this as t squared z square x squared, then plus tzxy plus tzyx, then plus y squared. That's just normal algebraic expansion. But in the case of expansion in inner product, it's not the same. So this will be what? T squared z multiplied by the complex conjugate of our z, is z squared. Okay, then multiply by the inner product of x comma x, then plus tz inner product of x comma y. Let's clean that. Then the other one will be what? Plus tz, that is, this one is going to be what? Y comma x, if we look at what we expanded there, then plus it's going to be the last one. What we obtained was what? The inner product of y comma y. Okay, so this, if you look at this holistically, you observe that we have used some representation before. We said we have used some condition. We said absolute value of z should be 1, and we said that a should be equals to inner product of x comma x. So this could be less than equal to. Okay, because it's an assumption. You can't say it's equal to. I think yes, you can't say it's equals to. It will be wrong if we say equals to, because we have assumed it. So it has to be less than equal to t squared. Now z multiplied by the complex conjugate of z is 1. So everything here is 1. Hope you understand. Then the inner product of x comma x is a. You can see. Then plus. Now if you had this together, you have what? 2t, z. You can use the absolute value of x comma y. Because why? Why do we put absolute value here? Because the condition of these things, actually, there is transposition here. This is the complex conjugate of this one. So you introduce the absolute value just to differentiate. The plus what? Plus this the inner product of y comma y. That one is what? That is b. I hope you understand. Sorry, that's c. That's c. Okay, that's c. Now this one will now translate into what is equal to now a t squared plus 2bt. Why? Because before we said the value of what? If you can go back to what we have actually said before, we said b should be equals to what? The absolute value of the inner product of x comma y. If you check what we have as our assumption b, yes. So this will replace, this will replace that. That's why we're having what? We have a 2t here. Because multiplying this now by this, you have z of this now has become. And initially we also said, recall we said z of absolute value of x comma y is equals to the norm of, the absolute value of, z of the inner product of x comma y, that's a slip of tongue, is equal to the absolute value of what? X comma, absolute value of the inner product of x comma y. That's, Now that implies that everything here will now be that b. Okay? Because z of the absolute value of the inner product of x comma y is now what? Is now the absolute value of the inner product of x comma y. And the absolute value of inner product of x comma y is b. So the whole of this will be b. That's why you have 2t times b. That's okay. Then plus what? Plus, I hope you are following, plus c. So if for, this is what we call what? You can see that this is an example of what? Quadratic equation. So from quadratic theory, from quadratic theory, you know, if we solve this, we're going to obtain what? B squared is less than or equals to AC. Yes, this solution you obtain. Let me write it properly. You obtain, or we have that. B squared is less than or equals to AC. So if you use quadratic formula method to solve this equation, you are going to observe that you are going to get what? This. That is the discriminant part of the equation will give you this. And with that now, so that implies from here now, and say that implies what? And what was our B? Okay, B is what? The absolute value of the inner product of x comma y. Now square less than or equal to. Now A, what is A? The inner product of x comma x, then multiply by what? The inner product of what is your C? That's the inner product of y comma y. If you go back to the initial statement of our proof, you check, this is exactly what is there. So that implies that we have established the Cauchy Schwartz inequalities proof. It's as simple as this. It has a very, very numerous area of applications in functional analysis. I want to believe that you've been able to understand this simple proof with this simple logic. So don't forget to click on the notification bell so that each time I upload a video, you will be duly notified. I remain Dr. OJ. Bye.